Let's look at the 1.9 warm-up. I gave you a diagram of dots. At the beginning, there's 1 dot. At 1 hour, there were 7. At 2 hours, a total of 13. You were to make this into a table. So we have at 0 time, there's 1 dot. At 1 hour, there's 7 dots. At 2, there's 13. You were to look for a pattern. How do we get from 1 to 7 and then from 7 to 13? Yes, we go ahead and we add 6. When you're adding the same number every time, that is an arithmetic sequence. That same number that you are adding is called the common difference. So the answer there is 6. To write the recursive. So that means if I want to find the next term, I would start right here, which is the now. So it's represented by the f of n. I would go to the previous term's output, which is represented by the f of n minus 1. And then I would go ahead and add 6. So 13 plus 6 would give me 19 there. I need a reference point, so f of 0 is the best one. So the f of 0 is equal to 1. That tells me where to start. Explicit then looks like this. The f of n is equal to my 0 term, where the beginning is 1, and then we're adding 6 every time. So 1 plus 6n. Or you could have 6n plus 1. Then I gave you a number 4 table, and you were to look, how do I get from 2 to 8, 8 to 32, and 32 to 128? So hopefully you notice that we're not adding the same number. So maybe we're multiplying. It looks like possibly that's what we're doing. The way to really check it is to go ahead down here and check for the ratio. So you start with a number, and then you go to the immediate previous one. So 8 divided by 2. We divide because when you're moving down, you multiply. When you're moving up, you divide. So 8 divided by 2 is 4. I could jump down to the 32 and divide that now by 8, and that equals 4. If I take my calculator and I take the 128 and I divide by 32, I get 4 again. So there I have a common ratio, which makes this geometric. To write the recursive of a geometric, I write the f of n, so the now. So if I wanted the 4th term, I would go to the now, and then I would go back to the 128, which is the f of n minus 1 is the previous term's output, and then I would multiply by 4. And again, I need to know, where does this start? And then I go ahead and I want to write the explicit. So the f of n is equal to my 0 term, the value there, 2 times my common ratio. What are we multiplying every time? We're multiplying 4. And then notice it's to the nth power. Because we did use the 0 term, we can leave it as n. On number 5, I asked you to look at arithmetic and geometric sequences and give me some similarities and differences. So hopefully you know that they both have rates of change. However, with an arithmetic, we're always adding the same number, which gives us a common difference. That's the number we're adding. In geometric, we're multiplying by the same number, which is called a common ratio. We can graph both of them. However, the arithmetic will be very linear, while the geometric will be curved or exponential. We can write the explicit formula for both. In arithmetic, it's f of x is equal to something happening just to x. So we know it probably more familiarly with y is equal to mx plus b. If I were to write the explicit for the geometric, we start with the 0 term and we have our common ratio sitting here. That's the number we're multiplying every time, and then x now is my exponent. We can write the recursive for both. They both start off with the f of n is equal to the f of n minus 1, so the now is equal to the previous term's output. But in arithmetic, we'll see a plus a number out to the right of that. With geometric, we'll see a times a number out to the right of that. I also wrote that the arithmetic up here is always steady. The geometric is very exponential, so it starts off slow, but then it will speed up, and you can see that in the graph. Whereas the arithmetic is always steady and consistent there. So those are just some. You might have come up with more, and we'll take a look at them when I get back.